all 6 people. So this is going to be kind of homey. So maybe I'll start a little bit different. Get a little sense of where you guys are from. What do you guys do? Are you developers, DBAs? Yeah. Good to meet you.
Yeah. All of the above.
All the above. How about you guys? Databases? Awesome. So I'll try to make this interactive, given the audience, and try to mostly tell a story and answer questions. I had a problem that I was facing for a long time. I came into applications, and this was my problem. Well, not exactly this, but you go into a system, and you open the database, and you look inside, and there's all these tables in there. And often it was hundreds or even thousands of tables. And to get that system to really work became more and more difficult. The more tables were there, the more data was put into the system. And took me a while to figure out what it was exactly. And then it became clear that when you look at an application, you're modeling objects, right? Your developers that are building the application on top of your database are thinking about objects. They're thinking about users, they're thinking about customers, they're thinking about products, they're thinking about patients maybe. They're thinking about objects at that level. Then they map it into the database. And that mapping layer causes what most of us know as the object relational impedance mismatch, right? Anybody knows the term? I see a few yeses. My problem was that I had applications that had very, very complex objects in them. And the objects kept getting more and more complex, literally every day. Every month there was a new release, and they would become even more expensive because they would translate into more and more tables. So I was in New York at the time and wanted to do something about it. So moved back to MIT and lost my computer. Wow. And it survived. I have a 17-inch for sale if anybody's interested.
I don't think it's gonna be stable.
No?
On that, no, because see the problem.
Yeah. How about now? I'll take a chance.
Still works.
Surprisingly. You tape it in. So what I realized is that I was designing those objects, and they existed in all these tables that we saw before the explosion occurred. But what I couldn't do is I couldn't figure out where they actually fitted. If there was only a way to express the fact that these are objects that I'm trying to deal with within the database, then that would make a lot of sense. And that led to a concept that we call table grouping. And what table grouping does is something pretty simple, actually. Remember the schema that we saw before? So imagine that schema with a little bit more information in it. Information that tells me that this schema deals with users. And that users have a bunch of attributes about them, a bunch of related tables to them, like qualifications, like their memberships, like tags about them, like capabilities that they have, feedback that they got, languages or payments that they had, and details about those payments. So, it brings that level of semantics back into the database. So it looks nice, and it is actually nice to understand it visually. But what we realized is that at the core of the mismatch is the fact that what we do next in any relational database is we put each of these tables in a different location, right? We take this table and put it in somewhere on disk, somewhere in memory, and then the second table and the third table, and so on and so forth. So we normalize and we break apart that structure. And what we wanted to do was take a different approach, which is don't break it apart. Because if you think about it, look at this for a second. What you're looking at here is an object, right, with the different levels of an object. Make sense? So why store it in multiple parts? Why not take the user row and store it with all the other parts? Why not build a document from all these rows? So that was the basic thought behind it. And then a few years of working on it, and there was actually execution. So it's as if we were shuffling cards, right? Shuffling rows together. Instead of putting them in many, many different tables, let's just put them together, something like this. So if I have a users table and an order table and an item table, rather than having 3 independent structures on disk and 3 memory structures to support them, let's just have one that logically looks like a relational schema, but physically construct this object, construct this document, right? So let me show you what that actually looks like. You need me to do something?
You have battery life?
Yeah, I do. I'm good. So I'm going to open my terminal and do something that you all know all too well. And look at some of the tables that I have here. So I'm going to do that again. So I connect to the database. And as you'll notice, that looks pretty familiar, right? And then look at the tables that are there. And there's a bunch of schemas that I loaded here just for example. So if I focus on the first one for a second, then I have customers, and customers have orders, and orders have items, and customers also have addresses. In a second, I'll show it in a slightly more graphical way, but I can do the same regular thing that we're all are used to doing, like select star from customers, I don't know, limit 10, right? And show me the first 10 customers, or in the small screen, select star from customers, where. So I can do all the regular SQL that you can imagine. And OK, fine until now. What I can also do is remember my data structures are different now. I realize that these tables together form a whole, form an object. So I can switch modes. And the way you do it is you set an output format to something else, like JSON, for example. And I can do the same kind of queries. So show me customer 2, and I'll get it as a JSON document, right? But it's just one row, and that's the response that I get. But now I can start doing much more interesting things. I can ask for a real JSON document. So for example, I can ask for the customer and all of its orders, just as an example. So select all the orders where customer dot customer ID equals orders dot customer as my orders. And let's see what I get here. So what you get here is a customer, which is me, and followed by my orders, right? And every one of the orders that I have as a document. The interesting part of it is that if you think about what's happening in the background, we're going to a single location, right, to get all the data. It's already co-located in memory. At the same time, we looked at it slightly differently, and we said, what if I went to my browser and wanted to do the same kind of thing? So I wanted to connect to my server and get, from the customer schema, customers table, get customer 2. And you can do that as well. So you can access the same kind of information in 2 different ways. So what you see here is the customer. Here is my record and my address and my orders, and each order has its own items, and so on and so forth. But the real insight here is that all this comes from the same location on disk, in memory, wherever it lives, right? So if we go back to what data really looks like, all I had to do was come here to get my object, right? So there's a bunch of ways that I think about table groups, but I talked before about the object relational impedance mismatch. So ways to think about a table group is it's just a bunch of tables, right? Together they have a meaning, but it's just tables, and you can look at them and query them as tables. It can also be seen as a JSON document or as an XML document, right? As an object, as a document that has a structure that you can access and traverse and work with. And you can also think of it as a denormalized structure. And the reason I say that is anybody who's done fact tables before? Anybody? Why do we do thank you. Why do we do fact tables? Because we don't want to pay that cost of joining the tables, right? So we'll put the data together so we don't have to do that. We kind of went for exactly the same win. We don't want to do these joins, but we also don't want to incur that redundancy that comes with it, that ETL process that comes with it. So different ways of looking at the same kind of idea, which is we can understand that an object exists in all these tables, and by putting them together, we eliminate the joins that happen either when you assemble an object or when you actually query the data. So that's great. So what? Why am I even talking about it? We have been building it over a bunch of years. As I said, it started from research. It went into a product. When you start thinking about how to build a product, how do you actually bring it to market? How do you build it in the right way? And what I've learned across time, having done a bunch of good things and a bunch of really bad mistakes, is that when you build anything like this in database space, there's a fundamental question that you have to ask yourself: am I after compatibility or am I after capability? And initially, when we did the research, we thought there's great tools out there. There's Postgres, there's MySQL. Why wouldn't I just go and use those tools, right? Why wouldn't I just build on top of them? And in fact, we tried. So we took MySQL and said, let's build a storage engine under MySQL. So we built this awesome infrastructure, this awesome storage layer that could do great many things. And then we discovered that through MySQL, it was choked. We couldn't get those benefits because MySQL thinks of the world in a very certain way, right? It thinks about tables. It doesn't understand the concept of, hey, this join is going to be free, or I can get an object directly out of the database. And so we realized that we would have to alter it in such a fundamental way that it'll be easier to start from scratch. In fact, we looked at Postgres and MySQL. We looked at a bunch of different options and realized that we really needed to build this from the ground up. And so that's what we did over the past 2.5, now 3 years. We've been building this from scratch, from the ground up. We've been seeing pretty interesting capabilities come out of it. What I want to talk about today is one specific element of what we developed. So this is the architecture, a little bit architecture, but mostly architecture of building an infrastructure based on a very powerful key value store. On top of it, everything needed to run a database. And on top of it, different interfaces. And now we're adding even more interfaces. One of them is a SQL interface. Another is the JSON interface. So you can access your data as JSON documents at the same time as you're accessing the same exact data as SQL. When we came to this specific point, we thought long and hard on how to pick a SQL wire protocol. And for hopefully this will be interesting for all of you. For me, it was another point of exactly getting to a decision: am I going to be compatible or am I going to be capable? Should I use something that exists, or should we build this again from scratch because we really needed to understand what it is that we do? When we thought about it, there were a few kind of options that kind of came to the forefront, right? One is MySQL. At that point, we knew MySQL pretty well. There's lots of drivers. There's lots of complexity in those drivers, and it's compatible both backwards and forwards. So every driver in MySQL has to work with every version of the server. That turned out to be a really big undertaking to try and implement that protocol to get those drivers. So one of the people we had spoken to, one of the friends that I gained from that experience is the CTO and founder of Continuant. He was the founder. And they went exactly through this process. So Continuant do you guys know what Continuant does? So it's a replication solution for MySQL. And to do that, they had to plug in at the protocol level, right, to capture all the messages. And to do that, they had to learn the protocol and every version of that protocol, which proved to be the most difficult part in their process, surprisingly enough. So then we looked at Postgres, and we found very clean BSD drivers. And most importantly, we found a spec that actually made a lot of sense. You could really see what the messages were. Not only what the messages were, what the sequence of messages were. So, put yourself in my position. You look at it and you say, what are my options? Take one of these, and then you gain the benefit of drivers that already exist and work. Or I will have to go and build my own drivers, but I have the freedom to do whatever I want with my protocol. The reality is that we chose Postgres, obviously, and we were really pleased and thankful for all the work that was done there. It doesn't satisfy everything that we want to bring out, and this is part of why I'm coming to present here. We'd love to see how to take it further, but it was a really pleasant experience. So the general approach is to build a network server that can speak the protocol. So our own stack is full Java, and to do that, we had to literally go in and learn the protocol, and it's surprisingly simple and surprisingly efficient in terms of the amount of code that was needed to do that. So I'm actually, considering the audience here, I'm actually going to show a few examples and then talk about a few of the lessons that we learned doing this. Before I continue, any questions? Fair enough. So what we did is we built a branch of the product that is dedicated just to speak the Postgres protocol. So it's probably a lot deeper than what most of us would ever want to go into, apart from maybe yourself. Have you worked on the network level itself?
No, I don't usually work on query planner stuff.
Okay. So it seems like there was a lot of work that was done there, and then a lot of different people that did drivers for different.
Well, everything at this point, pretty much everything goes through libpq except JDBC.
I think PG-8000 also is native. From everything with the Python driver. But I think you're right. I think also JDBC may be independent as well.
Yes,
well
JDBC has always been independent.
Right.
For a bunch of reasons.
So what we wanted to do was get to a point that people from any framework, from any language that they use, can actually access the data using as if it was Postgres. So we built. I'll actually go through the process. We built at the first a Postgres server, and the server literally listens for Postgres messages. It's surprisingly little amount of code and very, very simple to implement. We then map the messages. So what I'm looking at here is kind of the types of messages and the implementation. And again, the standard and the way the messages are implemented follows pretty well. I'll talk about specific instances. The other element of it are data types. And if you kind of think about it at the higher level, that's what a protocol does. It's messages that transport data and data types that describe the data that gets transported. From there, we went into obviously execution and then outputting the results. So one of the interesting things that we had to deal with is how do you output the data? The first thing we did was a row outputter. So the outputter is an abstract class and can be extended, and we extended it in different ways. The first way was let's build a Postgres row outputter. What it does is it behaves exactly like Postgres. It just returns rows in the appropriate data types, right? Pretty simple. Then we had this problem of how do we extend this further? So now I don't just want to get my customer back. I want to get my customers and his orders and his items back. In a relational system, the only way to do that, there's basically two ways. One is do multiple queries, right? Each query will go to a different table and bring back a different result set, one for the customers, one for the orders, one for the items, or write a single query that materializes the results. It's pretty simple when you have just 3 tables in a single branch like that. If you have multiple branches, that becomes very difficult. What do I mean by multiple branches? A customer has many tables related to it, right? If you materialize that, it would be a huge result set. So we started thinking, how could we leverage this work that we did with the protocol to bring back, we call it a nested result set, an object, basically. How would you do that? And there were 3 options that we thought about. The first is using the array data type. Did anybody ever use the array data type? I'm sure you have. So the array data type is I'd almost say it's similar in some respects to what we do. You can have an array as a type of a column, but it is fixed, right? The data in it is fixed. It's not as easy to query. And the result set, what we found in the drivers, is either it wasn't implemented, or when it was implemented, it's hard-coded. The structure of it is hard-coded. So we saw that. We decided that we don't want to try and extend every Postgres driver and every Postgres implementation that we have out there. So we tried to think of other options. The second option we came up with is, let's just resort to JSON as the format of data that gets transported from side to side. So how would you do that? How would you take a Postgres protocol that knows about data types and knows about messages and knows about rows that it returns and knows about result sets and coerce it or convince it to convey JSON over the wire? And we did it in the simplest way possible, which is you simply take every document, every JSON document that gets produced, and you convey it as a blob using that protocol. So what we get as a result set is a list of, or a multiple rows. Each row has a blob in it, which is a JSON. I thought it would be very expensive to do that, but it turns out that when we stress the system and really load tens of thousands of concurrent threads running against the system, it actually scales really well. And the extra cost that we have in preparing those objects and sending them is reduced by the fact that the network, the Postgres protocol, has to do very little work. It defines a very simple result set and just puts them over and sends them over. There's very little formatting that actually happens on our Postgres side or on the driver side. The last direction that we're taking is trying to be a little more elegant about it. And this is one of the things that I was hoping that perhaps some of the Postgres people would have ideas on. What we are doing is using a serialization mechanism. So we already have documents, right, that we convey back and forth. We wanted to serialize them in some way that makes sense and saves a lot of that work. And there's, at this point, many serialization libraries. Protobufs is probably the most famous one. We use it internally, and so we decided to try and use that instead. So we send protobuf messages across the wire using the protocol. And in terms of the efficiency of serializing and the overall cost and network bandwidth that it takes, it seems like a really good compromise. But it's definitely something that I was looking for the most elegant solution to get to without actually changing the protocol too much.
I know at one point we talked about multi-set support. Whatever happened to that?
I think we kind of decided that you can do it with a stored function that returns a set of cursors, and maybe that's good enough.
I think the problem with it require a protocol change, so nobody actually wanted to do it. Yeah.
Right.
We were following that.
At least not until we had full stored procedure support kind of on the back end. Because there's talk about, there's a whole concept of something called the multi-set. And it's something used fairly frequently with, a couple of the other enterprise databases where you can call a stored procedure and the stored procedure may
That's right.
return multiple sets of rows.
That's right.
Different Robert said, there hasn't been a big push to adopt that because it would require a protocol version bump. And until Postgres has multi-sat support in the stored procedures, there isn't a strong motivation for it.
Can't some databases return multi-sets from a query though? I didn't
Yeah.
think stored procedures was really.
Advanced revelation allows you to do this.
What does?
Advanced revelation database. It is pretty much like YAML database, it's markup database. So it is pretty much what you described, which allows to have table with subfields, 4 levels, pretty much what you present.
The only one that I know that tried to really do this is Oracle. So I had experience with it.
Did not, they tried, but they kind of
Abandoned it.
stopped the project,
That's right.
right? Because it's become
So the only ones that kind of remain are the multi-value.
yeah, so 2 databases, one is in Europe and other is here in the States. Advanced revelation using for government, pretty much, mostly
That's right.
in military, and DRAMs, it is,
Right.
yeah, so that's what they do.
So what we're trying to figure out is the best way to work with Postgres to get this working. Right now we do it literally at a level above it. So trying not to change the Postgres protocol too much and just to work on top of it. And maybe that is the best option. But we have looked over the Postgres protocol. And, we haven't been in the Postgres community as many years as some of you guys. But we haven't seen a better way right now to do this. So if there's any insight on it, we'd appreciate it.
A thought that I've had for some time is, if you look at a normalized design, you have something like, in your invoice table, you have customer ID, which is a foreign key to your
That's right.
customer table.
That's right.
Well, what if you could do something in a query like select from invoices, and you're selecting customer ID dot some set of fields in the customer record, so that one query, and without having to specify joins or anything, you could actually reference into a foreign key field as if it was a complex data type.
Almost like an implicit join rather than an explicit join. We're actually working on that right now. So it's somewhat of a different topic, but I'll show you what we are working on. So I'll make this a little smaller. So the way the system works right now is if I take a very simple query, and let's look at it for a second. So select all the names of customers who join with orders, join with item, and they have item quantity equals 5, right? A very simple query. So I'd run this for a second, returns 2 results. I'll actually set, I'm going back to table mode. If I explain this query for a second, then what you'll see is that the execution plan has no joins, right? So the execution plan is different than what you would expect from relational databases, because it starts with an index scan on quantity, as you would expect, where quantity equals 5. And then it does something called ancestor lookup. We just, now think about the object, right? I just traverse the object. So I have several operators that are unique to table groups, right? We've developed our own algebra to be able to traverse that structure called ancestor lookup, branch lookup. So the ability to walk your structure while it's in memory, while you're still working on it, without having to jump or join or do any other thing. So that's the way we develop the algebra. It means that if you have a 6-way join or an 8-way join, the execution plans only reflect joins that aren't embedded already within one of your objects, right? Only between objects, but not within an object. So a 6 or an 8-way join will be reduced to 1 or 2 joins, or however many joins are left in the system. So it's part of the efficiency. The second step that we wanted to do was exactly what you said. Take this query, and this is actually work in progress. Take the same query and write it without having to explicitly call out the joins, but say, select the customer name from customer C, where customer.order.item.quantity equals 5. So through that, you actually traverse your structure, right? So you explicitly are referring to the join, but you're not explicitly setting all the joins. That's what you were talking about, right?
Similar, I was thinking about it in the select clause context, but there's multiple different ways I think you could do it, and probably multiple different ways that make sense depending on what you're trying to do. But I think, to me, the key concept is to have the database understand that these may be two separate tables.
Right.
But, you know, the fact that you've set up this foreign key, that means something.
Exactly.
You should be able to simplify the SQL that you're writing because you know there's this relationship.
Right. So simplify this, get the semantic meaning to that you do while you declare the database to actually avoid having to write. So there's one problem there, which kind of makes me hesitate to use it. The whole beauty of SQL is that the idea is that it abstracts you from how data is actually stored, right? The whole idea of data independence goes back to Code's writing. What that means is that if it doesn't matter how data is stored, where the tables are, what indexes exist, you can write the same query over and over again, and it will just work. If you start using implicit joins, it means that you're counting on those joins existing either within the database or within the structure. So as long as we can make sure that, irregardless of what's, in my lingo, grouped or not, the query result will be the same, then you're true to that idea, to that fundamental concept.
I guess I'm not sure why you would be losing that, because today you have to explicitly specify all those joins.
The foreign keys, that's right.
Which means if the structure changes, really the only difference would be today you can remove your foreign key constraint.
That's right.
That's all it is.
That's right. It's just another index that verifies that constraint
it's
exists.
Not necessarily an index, but
Right.
It's a constraint.
Whereas
what I'm suggesting means that, and perhaps it would make sense to have a different term that implied there was a foreign key constraint but meant something above that, but that really gave the formal knowledge of an invoice is a sub-element of a customer.
Right.
You pretty much you pointed to data hierarchy somewhere. There is a hierarchy between data relations, some kind of relations, right? Between two objects or between two subsets. That's subset, right?
Yes, but doing it via a relationship that's formally declared at a structural level, instead of having to specify that relationship by hand every time you query.
So this really aligns with the way we think about it. So when we think about that nesting, we define it using foreign keys. They're just a special type of foreign keys called grouping foreign keys. Which is similar to what you're saying. So that semantics is right there, and so that we can interpret it into the language. But what I want to make sure is there's another way to specify this command. The command is alter group add table or alter group drop table, and all these commands do is basically add this grouping foreign key or drop it, influencing the way data is actually stored, right? So it comes at the physical level. I just want to make sure that whatever happens, if I drop this grouping foreign key and suddenly addresses is not under customers, that the query, as you specified it before, still works. In the same way that if you drop an index and you run a query, it still works. So the syntax has to be independent enough from how the data is actually grouped.
Right, I guess that's where, to me, grouping is there's a stronger inferred relationship.
Right.
Whereas I'm thinking of it strictly from the standpoint of this is how you can join tables together. So it sounds like you're grouping, you're trying to kind of put a layer on top of your table storage to represent a logical object, which is good and interesting. I'm
I got it.
And I agree. I think that you could certainly potentially run into problems tying those two together because,
Right.
you know, what really belongs to a customer logical object, do the invoices really belong there?
Right.
Or do they belong
On the,
somewhere else?
or a better example, a real many-to-many relationship. And where does that belong? And potentially it belongs to both. Right.
But now the flip side is, I find it highly unlikely that you would do something like, oh, invoices are no longer related to customers at all.
Correct. Because if they don't have a customer ID, then the whole meaning of what an invoice is goes away completely. Right. That's exactly what we see. So most of the schemas that we see when we start looking at it through our lens, they usually fall into 3 or 4 or 5 main objects in the database. Right? So if you take a look and there's a schema and there's 200 tables there, they actually form pretty nicely into a few main entities. And the decision points are just between those entities, decision point of where the tables belong. So usually it's a pretty easy decision because you just look at the usage of the system and that will give you the answer that you want. In terms of, you know, you have a many-to-many relationship, where would it actually go? There's, maybe I'll give one other example of that, but there's one other topic that, that we were dealing with, and I want to jump to for a second. So another, actually I'll just mention this. One of the things that really helped the process is Wireshark. I don't know if anybody's using that, yeah? But
I have in the past. Is that the same thing that used to be called Ethereum?
yes.
Okay, yeah.
So to track messages, to track network traffic, it was awesome. The kind of things it allowed us to do is look at messages in flight and look at where we got it wrong, where the formatting was wrong, where it didn't fit either the protocol or the way the drivers were implemented, and really work on it. It also allowed us to find things like there was a setting of TPC no delay that always waited a few milliseconds before actually flushing messages and sending them over the network. So it was really a godsend to understand what was actually happening between the Postgres drivers and what they expect the server to do. The other, so we had 2 big topics that we needed to really resolve. The first one was this idea of how do you return an object from a relational database. And the presentation this morning, if you guys were the first presentation, the keynote presentation, kind of the you know, post-SQL, if you will, he wasn't actually asking for that. He was just asking to make the database more malleable, right? Less tough with us, if you will. But for me, one of the biggest things that I wanted from database is to work with objects as they are. Not to ignore the fact that there are objects there, but to embrace it. So nested result set was the first thing that we really wanted to solve. How do you insert an object and how do you get an object from a database in a single request? The second was how to deal with metadata. So for Postgres people, there's drivers and they use the metadata in Postgres. But when you start looking at it, it seems like every driver, every ORM, so for example, Squirrel, etc., uses the metadata in a different way. So they have slightly different variations on a theme of how to query the database, the information schema, to get information from out of there. There you go.
There was a project that was started like, I don't know, 5 years ago. I think you were involved with what the heck do we call it? New sysviews. So the idea was to try and come up with something kind of like info schema, but that had all the Postgres specifics. And that is probably to me, that's probably the best way to answer that one, is to provide people, you know, here's the standardized way to get information without dropping down to the raw catalogs that can end up changing over time.
Right. So a view layer that provides a standard information schema and telling everybody, please use these unless you can't.
A Postgres specific
standard. Fair enough. Yeah. So we've thought about how to deal with it. So what we did was create views on top of our information schema called PG underscore whatever. And that's how we handled it for the most part. But sometimes even that didn't help because you had very specific formatting of queries. So we have a whole set, unfortunately, of queries that we catch in flight from different tools, and I'll give you an example. And I didn't know about the project that you mentioned, but we would literally parse very specific requests, and we have less and less of these, but literally do regex and figure out what the request is, and then figure out the right way to get that data out. We've been moving away from doing that because we want to standardize on using views on top of our information schema, but it hasn't been easy because of the very specific ways that queries were written against the information schema. So it would have been great to have that project, just from my perspective. But kind of at the top level, I don't know if I have this slide here. At the top level, it's been a really pleasant experience working with the Postgres drivers. They were amazingly friendly to write to for something that is pretty complex. I have some of our customers that are using the system fully from an HTTP perspective, so a REST API, and only access the system in that way. And what that made us do is extend constantly what can be done using the REST API. So how much information can you get out of it? For example, can you see an information schema? Can you describe the table? So suddenly we can get one result set that is schema. For each schema, the groups within it. For each group, the tables in hierarchy. For each table, the columns and the indexes, et cetera, and everything related to it. So I see people starting to move in that direction, and it's more pull to us than push from us. Because I think I come from the same, this is how I do SQL, I use drivers, and this is how things are done. But I'm seeing more and more of pull towards this direction. And so I don't think this is going away, but I think there will be a balance of how much we need to or can invest to get more and more and more tools working with the Postgres driver. So the last thing I wanted to show is a use case. Before I jump into it, any questions from you guys? Ideas? How does this, I wonder, there's database people here. How does this resonate with the systems that you guys work with? Do you usually work with operational, analytical systems? Have you seen this before? Does this resonate with some of the stuff you've been working on? You guys?
I have not really pursued this because it's just kind of ugly to try and do it. If you wanted to try and do this, you would, well, the only way you could really try and do this with Postgres right now is to do things like return an array of a table type, which
It wasn't designed for it.
you can do it, but yeah, it would become so difficult to work with that at that point, why bother?
Yep.
So that's kind of what was driving my desire for, let me do select flaw and let it figure out partially the join, but also just being able to do that kind of referencing.
Intuitively.
Especially like the multi-set stuff, or not. See, this isn't really, I don't view this necessarily as a multi-set problem. I view this as you want a protocol that allows you to return nested sets.
That's right. That's exactly right. That is not what the relational database was born to do.
Which
it is set, right.
That's really what
it's set, right? It's all mathematical sets that we manipulate, all relations, but it wasn't designed to return that kind of results.
The storage is all, this table, foreign key, this table, foreign.
you know that semantics, you just don't take advantage of it.
Right.
Exactly.
So that I think would be a very large leap forward when it comes to SQL.
It would be like having a relational database and not a SQL database.
Yes.
Yes,
Exactly.
which is what we're trying to do. So,
Soak the flames of relational
wha- one of the things that convinced us to not try to take something like Postgres is a car. You can't turn it into a bicycle. You can't turn it into an airplane. It's not the same thing. So one of the things that we do is we have operators that deal with different row types flowing through the system, right? Because the algebra is designed for it. So I can have a customer row flowing after and right after it an order row, and right after it an item row, and I deal with nesting at every level, from the storage to the operators to how the execution actually flows, all the way to the result set. So to change that kind of thinking internally, so to your point about about relations, about sets, these are just different. It's a set of heterogeneous items as opposed to homogeneous items. You had a question?
Yeah, sorry I missed the first part of the talk.
That's fine.
You already discussed this, but nested sets like that seem like they might be an ideal alternative to outer joins and that kind of thing. Did you discuss that? Aggregation on, say, an empty table versus a null values?
I did not yet. So there's a few kind of really obvious uses for what we do. We've been working with ORM developers. So for example, in the Python community with SQL Alchemy quite a bit to get them to use this. But that's more on the object access side, right? So instead of an ORM having to decide how to go many times back and forth and what to prefetch and not what to prefetch, a single request is all it needs. And it costs about the same. It doesn't matter how much data is in there, right? Because it goes to a single location. In the same way to do a transaction on it. So to put all of the data for an object, even if there's many changes, it all goes to a single location and does that using a single request. And it actually took a while to get to the point that using the Postgres protocol, we could actually do that. I think the question you're asking is more in terms of outer joins and queries that you can run on top of it that can become very efficient now.
Yeah, or maybe not even just more efficient, but might make more sense in some contexts. Might be easier to reason about. I know some of the relational theory, proposes that kind of a system as an alternative to an outer join.
So there is actually something we have done for outer join that we've seen a lot, and maybe this will give you an answer, but it'll hopefully give everybody a bit of a sense of how we are thinking about it. So what I covered in the beginning is that the core concept is table groups, right? So you figure that these tables of the user and all the related entities belong together. And this is just like, for example, LinkedIn, right? Think about LinkedIn and the way they retrieve a user to show you on the screen, right? What they do, they go to all the related information and pull it all. Of course, they pre-materialize everything because that would be too expensive, but that's the kind of idea of what happens there. What we realized is that, you're right, sometimes there are outer joins, either left or right. We hardly see outer joins, full outer joins. What we've actually developed is an ability to create indexes that span multiple tables. Because if the tables are already stored together, it's not going to be a lot more difficult. In fact, it's not difficult at all to have an index that is on user.name, qualification.something, and request.something else. So you can have indexes that cover as much as you'd like. You can define those indexes with left or right outer joins as well. So they will come to the data from this perspective or this perspective, right? So you could ask, I want all the qualification whether or not they have users, or I want all users whether or not they have qualifications. So we allow to leverage indexes for that use case. The other thing that is interesting and is a little beyond what you were asking is we discovered that with the way we actually store the data, we can take indexes that live across this table group and intersect them. So say I have a few indexes for each one of those tables, and I wanted to get all the people who live in city Chicago have a feedback of over 5 and have a tag of dog lovers. You can actually use 3 independent indexes, and each one of them points to a subset of the users, right? And then intersect them, like intersecting vectors or sets or whatever, to find the result set without ever touching the data. So what we've found is that we see more and more situations where it doesn't matter how complex the query is, you'll get an execution plan that can span, you know, this is a simple schema, relatively speaking. We often see objects of, you know, 50, 60, 70 tables, and any query on top of them, irregardless of how complex it is, doesn't actually have to do any joins. It'll use as many indexes as it makes sense, and then have one, and then has navigation within the object itself rather than having to go and join. No, the total, we have done stress testing. We just completed a pretty interesting experiment with Intel. They've given us, I guess that's the way Intel works, but they just said, hey, here's a couple of machines. They gave us 3 machines. Each one of them has 1 terabyte of memory, and said, let's see what you can do in that. So we loaded a lot of data on that, several terabytes worth of data. The thing to remember is that the total size of data is equivalent to what it would be in a relational. It is equivalent to a relational system, because every row is stored exactly once, as opposed to, say, what we're used to from fact tables, right, which usually explode very rapidly. So you get about the same efficiency of storage. The memory characteristics are very different. So I can give you the report later if you're interested, and you'll see how that works.
No, I investigated as well. So probably covered this already.
That's it. I'm not going to talk about it then. It is free and being open sourced as we speak. So we've been open sourcing from the ground up, just eliminating dependencies and open sourcing. The company itself is built on the idea that this is a tool that is useful, especially when you consider now NoSQL and SQL, right? And we want to do this, but we really like this. What if you could just get the JSON document, and you can get this, and you can scale? So the idea is the core product, the kernel, and a bunch of modules around it are free. There's specific modularity that's built beyond that for enterprise applications. And I can give examples, but those are modules that, you know, are in the enterprise edition. Yeah?
Have you looked much at Postgres table inheritance and how that might play into this?
Yeah. I have. I can't say that I've, you know, I'm not a Postgres expert, though I know a thing or two at this point about Postgres. Table inheritance is a great way to extend tables, right? To say you have a base table and then extend. I've thought a lot about abstraction, right? When we write object-oriented programs, what do? We say there's a class of animal, and then it has whatever. Vertebrate has different classes, and then underneath it has different things. And they all share some properties and then extend that. What I've seen a lot of is ORMs doing the wrong thing. The wrong thing is, let's create a table for each level of abstraction, right? In relational terms, join madness. Why would I ever do that? I'll get like 5 levels of joins and 5 tables just to get the data.
Well, because most databases don't have inheritance.
True. However, if you think for a second about what we do here, if I had that inheritance, those joins are free. Because I'll have animal, it'll be collocated with whatever it is, right? And you'll have the levels there. So those joins are inherent as part of the group structure, right? So I don't have to be afraid anymore. So one of my mottos is renormalize rather than denormalize. Don't be afraid of tables. In fact, we have 2 slogans. Don't be afraid of tables and don't be afraid of indexes. Because usually that's what we say, right? I don't want more tables. I don't want more indexes. Both of them hurt me. And we're trying to get away from that. So just in general, people, even when they use ORMs, they go, you know what? I don't know if I want this extra table. Just more pain, just another place that I have to go and get the data and put the data in. So they'll do a lot of things, denormalize in many, many different ways, right? I'm sure you have all seen the location 1, location 2, location 3, location 4 in the same table, right? So part of what we're trying to do is not be afraid of that. Yep, I think time is up. Any last questions? Cool. Thank you very much.